Hi, everybody, and welcome to our latest edition of our Hangouts with Sigma Xi's Distinguished Lecturers. I'm Fenella Saunders. I'm the managing editor of American Scientist magazine. And I just want to remind you that during this talk, if you have questions, there is a Q&A bar on the right side of your screen that you can turn on, and you can submit questions there that we can relay to the speaker during this session. If you are a Sigma Xi member and you have questions after this talk, you can go to Sigma Xi's online communities page, the lab, and submit your questions there, and we'll relay them to the speaker. So today, we're very fortunate to have Michael Spencer, who is a materials scientist at Cornell, and thank you so much for joining us today.
Thanks for having me.
So, what we're going to start with today is one of your areas of research, and that is two-dimensional materials, which sounds odd to a lot of people because they think, how can any material be two-dimensional? So I wondered if we could sort of define that term to start with, about what makes a material two-dimensional.
Well, most people call a material truly two-dimensional if the thickness is on the order of a couple of monolayers. The physicists among us will be very specific and define graphene as a single monolayer of carbon atoms, but we broaden it out a little bit to say multiple monolayers often.
Okay, so when you're saying a monolayer, that's something that's one molecule thick?
One atom thick, yes.
One atom thick,
Mm-hmm.
Which is about as thin as you can get.
Yes, about as thin as you can get.
Okay. When were these two-dimensional materials first developed? How long have they been around?
Well, surprisingly, when people look back at the history of, in particular, graphene, which is a prototypic material, we find that it goes back quite a bit. But what happened was that people identified them without separating them. Allison Blakely at Cornell identified two single crystal graphene on top of a metal. People in the silicon carbide material science research identified, conditions which silicon would be removed and graphite would be left, and it was one monolayer thick. But the explosion of interest came from Geim and Novoselov when they were able to demonstrate techniques that peeled off a single monolayer of graphene, and then they were able to do experiments to analyze it and understand it. Surprisingly, everyone, even non-scientists, have been doing their experiment for hundreds of years and not even knowing about it. When you take an ordinary pencil, sometimes you can actually get one of pure carbon, and you write on a piece of paper, you are exfoliating little thin strips of carbon, and if you're lucky enough, some of them might be a monolayer thick. What Novoselov and Geim did is just do it in very, very, clear research conditions and repeatable ones.
Right, and just for people who are interested in more background, we'll have a tweet up to a link to an article that has a lot of the background on the development of graphene and how it's produced. So if you're interested in knowing more than we cover here, that's an open access article that you can read anytime. Just to go back to what you were talking about, just for people who are wondering what graphene is, as I understand it, graphene is just sort of a single layer, and when you build up those layers on top of each other, that's what actually makes graphite, is those layers kind of all stacked together.
Right, that's right. The stacking patterns in graphene are not regular usually, and so graphene is usually what's called turbostatically stacked, and that's the usual way we find it. Although in graphene you will often find ordered stacking layers, which can be exfoliated and form either monolayer or bilayer graphene.
Right, okay. Now, graphene itself is kind of forms from these, hexagonal molecule shapes of carbon in a single sheet. So graphene is all carbon. Are there other two-dimensional materials that are not all carbon?
Well, yeah, the field has now explored many materials that are not carbon, that are labeled as two-dimensional, and in truth, the unit cell is multiple layers of material. Among the most popular are what's called the metal chalcogenides, and usually they have a metal layer surrounded on the top and the bottom by other molecules, the chalcogenides. The prototypic example is moly disulfide, and if you look at the material from the top, when you project it downward and sort of mentally squish things together, it looks a little like graphene, but it is actually three layers of material that form the unit cell of what's we refer to as moly disulfide. There are now other examples of two-dimensional materials. A whole smorgasbord of them, so to speak, that are being investigated or proposed to be investigated. Even silicon is supposed to have a two-dimensional form, silicene, yes.
Right. Okay. So one of the proposed uses for graphene that's gotten a lot of attention is for its use in electronics, specifically in transistors. And I wondered if you could talk about what would give it an advantage over traditional semiconductor materials in terms of, why this one monolayer thick material would have an advantage over a thicker one in that kind of application.
So I'm really an electrical engineer that's working at the nexus of materials in electrical engineering, and graphene has both an allure and a major problem. And the allure of graphene is that it is got a tremendously high electron velocity that has been realized, almost 10 to the 8th per centimeters per second, which is about the fastest an electron could move in a solid. It also has an extremely high electron mobility, which is the ability of an electron to respond to an electric field. Both of these
I wonder, I think we lost you there for a second, Dr. Spencer.
Am I back?
Yes, you're back now. But you were just talking about the advantages the graphene has.
Right. I had talked about the speed of the electrons. I don't know whether you got that part.
Got that, and the mobility.
And the mobility. So the next piece that's very advantageous is because it's one monolayer thick, the electrostatic control, that is the ability of a control electrode to modulate the electron current, is wonderful. And the last thing that it's really good, the allure of graphene, is it can handle a very high current density because it's such a robust material. The problem and the frustration in science is that this material does not have a band gap. And so without an electronic band gap, it's very difficult to make devices that really 100% turn off. That is, if you apply field to the control electrode, can you get the current to essentially zero? That's never been possible with graphene. And so there, over the last, maybe 5 to 10 years, people have been trying as hard as they can in various ways to give graphene a band gap. Unsuccessful right now. So the big application, the transistor application, is elusive. What has happened is just the application of graphene as a transparent electrode. There, you have some real advantages, and there's some interesting things that one can do. We did a demonstration with colleagues in biology where we use graphene to go into the gut of a mouse, and you can measure neuron activation using these electrodes, and at the same time you can stimulate the system with light simultaneously, so you can get light-induced information and coordinate that or correlate that with electronic information. Very hard to do that with any other material which is biologically compatible, transparent to light, and has low resistance electrodes. So there, graphene has shown some advantages, but the investment in graphene was really for the electronics industry to be a new type of transistor.
Right. Okay. So just to clarify what you were saying there about transparent electrodes, the reason it's transparent is simply because it's so thin?
Yes, that's correct.
Okay. And just to back up for a second and to talk about band gaps there, the reason that you want a material to have a band gap, is that related to sort of this binary nature of transistors where you want them in either an on or an off state to store information?
That's right. Either on or an off state to store information, and for low power dissipation. So when you're not providing some functionality, you don't want to dissipate power. So you want them fully off for that reason as well.
Right. And so why is it that graphene doesn't have a band gap and other materials do?
Well, not every material has a band gap. Metals, for example, do not. Graphene is unique. It is a zero band gap semiconductor, and it is absolutely unique in that regard because all of the atoms in the lattice are of the same nature, and it just so happens that the wave functions sort of coincide so as to completely cancel each other out at the K point, which is where the lowest difference between the conduction and valence bands are. If you put a different material, so graphene has two sublattices, and if you put a different material on the sublattices, the big example is boron and nitrogen. So instead of having a carbon sublattice and a carbon sublattice, you can have a boron sublattice and a nitrogen sublattice. Exact same structure, boron nitride, almost identical to graphene. Because they're two different atoms, you don't get this cooperation with the wave functions, and as a result, you get a very, very large band gap, almost 6 electron volts. Rather amazing property of nature and materials.
Okay, so when you're talking about adding those other atoms and molecules in to the graphene, is that sort of the equivalent?
No, in the case of boron nitride, separate material, not added in, just something that you can also produce.
Oh, I see.
You can produce it by growing boron and nitrogen together.
I see. Okay, so that would be a different material.
Different material.
Right. So
exact same lattice structure, though.
Right. Okay.
And one monolayer thick.
I see. Okay. So that would be another example of a two-dimensional material.
Right.
Okay. Is it possible to do what they call doping to graphene, much like they do with silicon?
Yes, it is. Yes, it is. And interestingly enough, you can do doping in 2 ways. So you can do doping in graphene by putting some atoms to physically substitute into the graphene lattice site. What has been shown to work is nitrogen or boron, and that is fine. But you can also do, and this is even more interesting, you can do something called surface transfer doping. So you can put things on the surface of graphene, lots of different things. You can put polymers, you can put gas molecules, can absorb on the surface, and these molecules will accept or donate electrons to the graphene atom by a surface transfer phenomenon. The advantage of doing it that way is that the lattice isn't disrupted, and so the electron flow is not compromised.
Right. Okay, that makes sense. But even with the ability to do that, that still hasn't been able to produce a significant band gap in graphene.
Right. So that certainly changes the conductivity, but does not give you a band gap. For that, you need to have a fundamental change in the lattice. And it has to be very, very uniform over a large distance.
Right, which is a difficult thing to produce, I'm sure.
It's difficult.
So one of the other problems, I guess, that's been encountered with graphene is producing it in a uniform way on a large scale. I wondered if you could talk about some of the ways that graphene is produced and any that have been leading to mass production.
So actually, producing graphene uniformly on a large scale used to be a problem. It is now much less of a problem, and graphene is being produced on a large scale. There are several companies that will produce graphene and sell you, sheets of graphene either on metal or transferred to plastic or quartz that are in dimensions of feet. So the technique that has evolved is the growth of graphene on copper. And this was pioneered by Rodney Ruhoff when he was in Texas, a Cornell alumni, or a son of a Cornell professor. And what he discovered was that copper is almost the ideal substrate to grow graphene on it. The catalytic action of the copper allows the methane molecule, which is flowing as a gas over the substrate, to be broken down, and then the copper atoms then flow onto the surface and find each other and form islands of graphene, which get expanded. And through some persistent work by a lot of contributors, people have learned the right conditions of pressure and temperature and a few other little tricks of the trade. And now we can grow graphene that has grain sizes of 20 microns, which means that inside a 20 micron region, the graphene will be absolutely perfect. That's good enough for almost any application. It would be good enough for transistors if we had a band gap. And there have even been demonstrations, probably not of a production nature, but there have been demonstrations that show that we can grow this even up to a centimeter size of perfect graphene. So producing large areas of graphene is a lot less troublesome than it was before.
So just to go back and explain grains to people for a second, what you're talking about here are areas where the crystal lattice of the graphene, they don't quite line up with each other. Is that right?
Right, that's correct. So, so a grain is a region of perfect crystallinity. And when you have regions of two different regions of perfect crystallinity, and they're misaligned with each other, they will form boundaries. And this is the case in general with many kinds of materials, except the ones that have been researched so hard that we can grow large single crystal grains, single crystal regions. But in graphene, we're now able to grow these grain sizes, as I said, up to 10, 20 microns. That you can buy. There are companies in Korea and in the United States that you can actually buy graphene, and it's not too expensive with this kind of material. The problem is that once you get it on the copper, you need to remove the graphene from the copper so that you isolate it electrically.
So we've just had a quick question from the audience I want to interject here before we go on. We have somebody who asks, how large are the samples you normally work with and test?
So because we're a university, we generally, our preferred sample size is about 1 centimeter by 1 centimeter.
Okay, great. So when you're talking about growing these, the method that you're talking about here is chemical vapor deposition, is that right?
Yes.
And you're talking about removing that from the copper and potentially probably supporting it on a different surface that's not conductive, is that right?
That's right.
And I understand that when you do this, that sort of crinkling of the sheet can be a problem. And I know you've done some research in this area, so I wondered if you could talk about ways that you've been able to improve on sort of the crinkliness of the actual layer.
So in general, this area has been another problem which is kind of solved, is the transfer of graphene off of metal substrates. And again, a lot of good work by a lot of different people. The standard procedure, and there are variations of this, but the standard procedure is to coat the graphene with a polymer, usually polymethyl methacrylate, and then to put the material inside a etching solution, copper etching bath, and the copper will completely etch away, and the graphene covered by the polymer will float to the surface. And then you basically scoop underneath that material with your substrate of choice, probably glass, sometimes silicon, and you scoop it up, and it will then be onto the substrate, and after things dry, it'll be held quite tightly by van der Waals forces. So then you remove the PMMA and continue to process. And again, just experience in the industry, tricks, and learning how thick to put down the PMMA and so forth and so on. You can pretty much transfer without very much wrinkling, even over a large area. So it's, and by the way, the same process works for boron nitride and other 2D materials.
Okay, so most people know what van der Waals forces are, but just to give people a quick review, I mean, basically we're talking here about weak interactions between molecules rather than strong covalent bonds. Is that correct?
That's right. Right. If you put any material very, very close to to another material, there will be a weak interaction. You described it very well. And that weak interaction, despite being weak because things are so close, it's still strong enough to hold the material tightly onto the substrate.
But basically, there's no sharing of electrons between the two substances. That's what usually causes a stronger bonding.
No transfer of electrons.
Transfer. Okay. And when you're talking about removing the PMMA from the graphene, is that just done chemically?
Yeah, that's just done chemically. That's done with solvents, acetone, methanol. One of the problems with graphene technology is that what you usually would like to etch polymers off in a gas plasma, but in this case you can't, because the oxygen plasma normally used would destroy the graphene.
Right, okay. So when you're talking about actually creating these sheets of graphene, you mentioned methane, which is CH4, as the source of the carbon for the graphene. And one of the processes that's involved there, I think that you've mentioned in some of your research before, is it's a 2-temperature process where you have nucleation and growth at different temperatures. I wondered if you could sort of describe why you needed 2 different temperatures in order to grow these sheets.
Well, the process that we've been talking a lot about, sort of the standard process, is a growth on metal substrates. And typically that is grown at a single temperature. But we thought we would try to, in experimenting, it would be very nice not to have to transfer graphene. It would be very nice to grow it directly onto an insulating substrate. So we did a lot of work trying to understand how to grow graphene directly onto sapphire. And sapphire is a high temperature substrate. Now the lure, the attractiveness, the beauty of the copper technology is copper is a catalyst, meaning that it lowers the energy of decomposition of the methane. Without the copper, without the metal d electrons to catalyze a reaction, you're forced to use high temperature to break up the methane bond. So we had to go up to 1500 degrees C in order to break up the methane to allow it to deposit onto the sapphire substrate. And so in that case, it's more like a traditional growth where the temperature can be controlled, and you can have a temperature that's best in order to have low nucleation, and then a temperature in which there would be no nucleation, but only expansion of the islands. And that's a kind of a growth technique that people often employ in crystal growth. And we used it here. And
right. So the advantage there, why you wouldn't want further nucleation, is that would give you additional grain boundaries. Is that correct?
That's smaller grain size, additional grain boundaries. Same thing. Yes, that's right.
Okay. But with copper, you don't have to, you have the copper itself, you said, actually catalyzes the breaking up of the methane?
Yes.
How does that actually work?
Well, I'm not exactly a chemist, but the explanation that I understand is that d electrons in the copper are favorably interact with the methane molecule while it's on the surface of the copper, and that allows the removal of the hydrogens.
I see. Okay. So I understand. We were talking about graphene as being potentially, assuming these problems could be resolved, being useful in electronics, and you mentioned it as an electrode material. But are there other potential areas where graphene could be used? I mean, some people have mentioned them because they're sort of impenetrable membranes, so they could be used in other applications.
Yeah, again, it's intriguing. Graphene, and this was work done at Cornell by Professor Paul McEwen's group. They demonstrated that a single layer of graphene will block anything from going through it, and that's because the lattice is so tight, so dense. You can't get any gas through it. In principle, if you grow, for example, if you grow a layer of graphene on a penny and you put the penny into a water vapor atmosphere, the penny will not form an oxide layer because the oxygen can't get to the copper to oxidize it. So it has been demonstrated that graphene can be a barrier between vacuum and water, vacuum and solids, and it's pretty tough. It, however, is not, still, it's only a monolayer thick, and there are limits. And I think this application would be well served if we could figure out how to grow more than one good quality layer of graphene. The difficulty in 2D materials, it's a 2D material which is wonderful, but it's a 2D material which is terrible. It's also terrible because you can't grow multiple layers of good quality. You can grow this one beautiful layer on copper, but when you try to grow a second, or God forbid, a third or fourth layer, it really gets difficult quickly. Even on sapphire, we found that the quality of the layers goes down after the first really great, high quality, beautiful monolayer. So it's an interesting problem and a challenging one.
Right. So in this case, you would want more than one monolayer just for toughness?
Exactly. You'd want it for physical strength.
Right. Okay. There's also been some research into using it as an etching mask, which I thought was interesting as another way to kind of get it into the reduction maybe of chip sizes without actually being involved in the electronics of chips.
Yeah, again, it would be a really good material because it can be made so thin, so differential exposures are easier. A related application is using it as a holder for the T-transmission electron microscope, because you can essentially make a little basket of graphene. The holder does not block the electron beam when it goes through the test sample. So you can get, in principle, much better resolution. And in fact, people sell graphene for that application. But I think those are, while nice, interesting applications, they are sort of minor marketplaces if you're interested in the commercializing technology.
So do you still think that the area of most potential for graphene is for use in electronics?
Yes, but not as a transistor. I think there are going to be some new ways of using graphene, perhaps in plasmonic devices or as sensors. The actual traditional transistor without a band gap does not really work well enough.
Do you think we could quickly go over what a plasmonic device is?
A plasmon is a collective oscillation of charge, and graphene is a kind of material that produces these things quite easily, produces plasma. So if you shine light onto graphene, instead of producing electron hole pairs easily, it will produce plasmons easily. And these plasmons can be used to make optoelectronic devices. It's a very interesting area of research, and is one of the places where there's probably enough promise to really keep it supported.
So do you think that graphene research is one of those areas that's sort of been hyped up? It sounds like they're not really, the material's not living up to the potential that people have put into it.
Yeah. So, so yes, there's this Gartner hype curve that you can find on the internet, and in that curve there is the peak of unrealized expectations, and that has passed for graphene. We're approaching the trough of disillusionment, but I think there will be a region of enlightenment, and finally some solid applications for graphene that are unexpected. This is a curve that follows all technologies. This was sort of a standard curve, and right now I think people are very disappointed in the output of graphene. But I think ultimately these curves take about 20 years to cycle out. I think ultimately there's going to be some very solid applications. It's probably not going to be the the trillion-dollar industry that they were hoping for it to be. It'll probably be, you know, something much less than that. But it's going to be something. The material has just too many world-class properties. If you sort of make a list of all of the things that graphene does better than any other material, it's a pretty long list: thermal conductivity and mobility and electron velocity and so on. Also physical strength. It's probably the strongest material known to man, and on and on. So hard to believe that it's not going to find some place for it to be. More question marks would be for the other 2D materials. Actually, the other 2D materials have band gaps, but they really don't outperform anything. So that's been a bit of a frustration. The graphene outperforms of almost everything without a band gap. The other materials have band gaps, but you could probably find another material that would do just as good or better.
Right. Okay. And you mentioned, just to clarify there, the possibility of using graphene in sensors. Would that be a case where it was actually providing a signal of something electrically because it's got such great conductivity?
Well, no. This occurs because of the transfer doping. So if you put something onto the surface of graphene, particularly certain molecules, what is it, NOx, nitrogen and oxygen molecules work particularly well, you will change the conductivity of the graphene and therefore produce a change in the signal output. And for certain molecules, this is incredibly sensitive. You can actually go to the molecular limit. One single molecule can be detected in this way. So graphene as a sensor might be interesting because of that. And there may be some other ways to implement graphene as a sensor. It can absorb radiation uniformly, although small amounts of it, but it can absorb uniformly with wavelength, and that's good because you have a high spectral range detector. So again, it would be nice if you had multi-layers of graphene so you could get more absorption, but therein lie the challenges.
Well, of course, there's always challenges in any research, I'm sure. But I guess that just makes you feel like you have something to do. So, so I wanted to just switch gears a little bit here in the remaining time we have, and generally talk about some other thin film related research that you're doing in terms of power source and storage. One area you work on is called Betavoltaics, and I wondered if we could define that for people who don't know what that is.
Okay, so this is a much more engineering area, and actually a fairly old one historically. So everybody knows what photovoltaics are. They are the production of power, voltage, by the absorption of photons. And so betavoltaics are a direct analogy to that, but instead of photons, we absorb high energy electrons. And these high energy electrons are produced by radioisotope decay. If the radioisotope decay produces only electrons and not alpha particles or anything else, it's called a beta emitter. So beta because it's an electron emitter, and voltaic because it's producing a voltage after charge separation.
So you mentioned these are radioisotopes. What are the actual sources of the material here? What kind of materials produce these kind of beta particles?
So the most popular source that we use, and the one that has the commercial potential, is tritium, which is of course an isotope of hydrogen. And the tritium is in the gas phase, but to make a device out of it, we diffuse the tritium into a titanium matrix and form a metal hydride. So it would be titanium hydride or titanium tritide because it's really tritium instead of hydrogen. So this metal matrix then, which is almost 100% tritiated, is the source of the high energy beta electrons. And
okay.
you can put that right against your detector or
Right. Okay. So when you're saying that the tritium is being absorbed into the other material, is it becoming sort of chemically part of that material? It's not still in the gas phase at that point.
No, it's actually making a bond. So you go from titanium metal and you diffuse it at a modest temperature, about 400 degrees C. It goes into the matrix and bonds and becomes a metal hydride.
Okay. And because everybody still has a lot of immediate responses to radioactive material, I understand these kinds of radioisotopes are fairly easy to shield. Can you talk about how that's done?
Right. So the isotopes are shielded. The beta electrons are stopped very easily. For example, they would be stopped by just a layer of dead skin. They don't penetrate very far. And most people don't realize that in their homes or in their offices are beta emitters. They are in the smoke detectors. And the beta emitter in that case is called americium, and it emits high energy beta electrons, which are used to detect whether or not you have a fire. So you've been living with radioisotopes in your house and didn't know it.
Right, okay. So you mentioned that this is kind of an older field. You know, these devices have been around for a while. Can you talk a little bit about their history?
Well, when people wrote the theory about solar energy conversion, the original papers were actually radiation converters. And they proposed in the original papers that in addition to photons, high energy particles would also work as radiation converters. In the, I guess it is probably the 80s, people made Betavoltaic batteries out of promethium, another beta emitter. And these batteries were used to power pacemakers in patients. They were actually implanted, and they were a product. They're very limited distribution, about 400 or 500 of them, and but were cleared by the Institute of Health for that application. So this technology has actually been around a while. There were problems in terms of that particular implementation because promethium is a very high energy beta, and because its energy is so high, when the electrons decelerate, they produce something called Brillstrahlen radiation, which is X-rays. And those X-rays have had to be shielded. That made the device a lot bigger and more bulky. So these devices, the energy of the electrons is much, much lower. They don't produce any radiation. So the shielding requirements are almost non-existent.
So you mentioned the use of these materials, I guess, more traditionally in smoke detectors. Have there been other places where they've been used? One of the viewers is asking about biomedical applications, and I thought you might want to talk about their uses there because you just mentioned the use in pacemakers.
Right. So other applications, before talking about biomedical, other applications, actually production applications. Betavoltaic, or I should say radioisotope emitters, not necessarily Betavoltaic device, but radioisotope devices, are used in signs for environments that cannot tolerate open flame or open spark. So these, in this case, the high energy electrons hit a phosphor, and the phosphor glows. They've also been used in gun sights as well. That's a production product. The interest for them, the main interest for the Betavoltaic product is in biomedical applications for either pacemakers or for biomedical monitoring. In the pacemaker application is really ideal because as pacemaker technology has been developing, the size of the pacemaker has shrunk, and the amount of power required for the pacemaker to pace the heart is now much less than it used to be if it's now attached using the new technologies. So the form factor is much lower, power requirements is lower, and it's a pretty good match to what a Betavoltaic cell could produce. It is attractive, therefore, because of the lifetime, which is related to the half-life of the isotope, which is 12.5 years. So that's almost an ideal application. But there are others in biomedical that one might conceive of, anything that would be measuring pressure or perhaps temperature. Any kind of implantable device could benefit, particularly when you need to have a very small form factor and power requirements are modest.
So another reader is asking basically if there were any applications in things like prosthetic, I guess, limbs and things like that. I don't know if that's something that's even been considered.
Right. So one of the difficulties with choosing applications are the power requirements. And I would imagine that prosthetics would require too much power to overwhelm a Betavoltaic device. There are safety limitations imposed by the regulatory agencies about how much radioisotope one can use, allowed to use in these devices. And so when you do the calculations from that perspective, you get certain power limitations.
Right. So you're saying that their advantage is they have a long life, but they have relatively low power overall. And you mentioned half-life. Could we talk about that for just a second for people who have heard that term but might not really understand what it means?
Right. The half-life is defined as the period of time where a radioisotope loses 1/2 of its radioactivity. So that means that the nuclear reactions have been, half of them have been done. In this case, it's hydrogen going to helium. That would be the half-life.
So do these reactions kind of happen on almost like an exponential curve? Do they happen over sort of like a regular decline, or do more of them happen at the beginning?
Exponential.
Exponential.
It's an exponential. The radioisotope law is exponential decay.
Mm-hmm.
with a decay constant.
Mm-hmm.
And when the exponential is equal to 1 year or close to 1 year at the half-life.
I see. Okay. So what is the interest now in these materials if they've been around for a while? Have they had limits in the past? What is making them attractive at this time?
Well, what's happening is that the things are coming together. The electronics industry now knows how to make very, very exquisitely low power electronics. In the early 80s, the electronics, the electronics needed a certain current density to operate, certain power density up in the milliamp region. That's why we use the high power beta radioisotope was used, promethium. It's a very high power isotope. Now power requirements are much, much lower, orders of magnitude lower. So electronics is using less power. In addition, as in the case of the pacemaker, people have learned how to make smaller devices. So the footprint of devices has shrunk. So now it's time for a re-examination of this technology, because that's what it does well. It produces small amounts of power. It has a small power output, but an extremely high energy density. And the application space is now coming to meet it. It turns out that when you make normal batteries, like lithium batteries, small, there are certain limits. A lithium battery, just by the nature of it, tends to be a three-dimensional technology. And although they're very good, as you make them smaller and smaller, it becomes more and more difficult to make them perform as well as they can if they're larger. On the other hand, a Betavoltaic device is naturally scales to the smaller dimensions. So everything is sort of pointing in the direction of this being a more and more attractive technology. The other thing that's interesting to me is we're exploding into this idea of the Internet of Things, again, because of the low power requirements. And so the problem is that the computing technology and even the sensing technology can do most anything. Everybody's asking about the power sources. And so if you're talking about autonomous power sources, there are about 3 possibilities. You can have a miniature solar cell that would take light from the room or light from the outside. You can have a lithium-ion battery, which is pretty big usually. You can have a piezo electric scavenger, which will convert motion into energy. or you can have a beta-voltaic battery. Well, if you eliminate the lithium battery because A, it's not very long life, and B, it's big, and C, it doesn't work too well in relatively modest extreme environments of temperature. If you eliminate the lithium battery from the picture, you're left with the others. Well, the others are great, but if the sun's not shining and you're not moving around, they don't work. So my vision would be you would have a trilogy of sources, the beta-voltaic source being the source of last resort, which would keep the computer processor alive, and then you would use the sources when they became online, when somebody turned a light on in the room, or you started moving and something started vibrating, and you were able to get power that way. So you start thinking of micro power as kind of a micro grid with different sources being able to do the things that they do best.
So I'm wondering here, if you're mentioning them being used as batteries as a power source, can they be used for power storage as well?
Yes, they can, but it's a separate function. The beta-voltaic is actually a power generator, not a storage. But the power is always coming out. So if you're smart enough to capture it, you can capture it and store it in, say, a capacitor or a thin film battery, which is not like a lithium battery, it's a thin film battery, and then you can still have that power for another day or another time. And so if you have an application, say you have an application where you wanted to monitor the temperature of the agricultural field over a long period of time. So you would put a lot of sensors down, and you would have them take the temperature measurement, and making the temperature measurement and even making a record of that data doesn't really take much energy in today's world. You can do that with a beta-voltaic. But the readout, if you're doing it with Wi-Fi, does take a lot of energy. So if you only wanted to read it out once every 2 weeks, you could probably store enough energy from the beta-voltaic so that you could read it out in a couple of minutes, all the data that you stored in 2 weeks of work. And that's a good application because in this long-term monitoring, you need your monitoring for trends, not for actual data instantly. So that's a good application for it. If you wanted to have the instant gratification, you want to get the data right now, it would be a bad application.
Right, okay. So when you're actually producing these beta-voltaic cells, you're actually engineering the surface of the material to have this sort of pillared formation on almost the micro scale. I wondered if you could talk about why you're doing that and what advantage it gives the beta-voltaic.
So what you'd like to do is increase the power for these beta-voltaic devices. And unlike solar cells, your energy source is right next to you. It's this tritium, titanium tritide. So if you can modulate the surface, you create a surface with a large surface area, and so you can put more fuel on a given area of device by a factor of 100 just by etching the surface. So that's what one of our versions of structures is, to increase that energy by making such a structured surface. Difficult technology to do, but in principle, you can increase the power by a factor of an order 2.
So let's talk about some of the other potential applications of these beta-voltaics if they have this small footprint and they have this very long-lived, low power. You've mentioned a couple of places, but I think some other applications you've looked at are potentially things like RFIDs or tamper detectors or other things. I wondered if you could talk about some of those other applications.
Well, the other interesting application is anti-tampering. And there, suppose you had some box of electronics that you really didn't want people to look at. You have to be able to monitor and then set an alarm potentially when somebody opens it. So you need something that really doesn't have to have a lot of power, but just has to be on all the time to detect a breakage and then trigger an alarm. And for that, a Betavoltaic device is interesting. And the reason it's interesting over a battery is lithium batteries are not very good when the temperature changes. So Betavoltaics are, in fact, very resistant to temperature changes. So that's a good application. If you wanted to store a crypto key, in electronically, again, you want something that lives a long time, but almost no power output. You just almost need a voltage. So that's a good application for a Betavoltaic as well.
So just wondering, obviously these are kind of in development still. What are some of the limitations that still exist to producing these sort of on a larger scale?
So we have been able to produce batteries that are purely planar, and I think there are no more limitations to doing that. But the technology of actually making the batteries with the corrugated features is difficult from a lot of respects. In one respect, you have to pattern silicon carbide. That's tricky. And in another respect, you have to form the titanium tritide. And because when you form that material, the lattice constant changes, there's a potential for the material delaminating. So that's a problem. And then, unlike the situation with the very, very shallow junctions, the electron hole pairs that you create in the material, you want to harvest them to produce voltage and current. You have to make sure that you don't lose them by them going to the surface and recombining and with traps. And so the passivation of the surface of the silicon carbide has to be very good. So passivation, compatibility with titanium tritide, actual formation of the microstructure, they've all been challenges for us, which we have sort of dealt with one by one over the last few years.
Do you have a feeling for the time frame in which these batteries might become more regular, standard, or popular? Is there a sort of a time frame, like 10 years or?
No, I think that I think if the people, we have a small company, if the people are happy with us and we get an investment, I think you can get a working prototype for the medical area within 1 or 2 years, and a production prototype within 5 years.
Wow, that's pretty quick. Okay, we're very short on time right now, so just as a little bit of a wrap up, I thought we might just talk a little bit more generally. You mentioned that you work with chemists and you're more of an electrical engineer. I wonder if you could talk about working in cross-disciplinary teams and how that can potentially help speed up research. Has that been your experience?
Yeah, we're very lucky at Cornell. We've had cross-disciplinary centers for a very long time, going back to the 60s. And I think everybody who does cross-disciplinary research is sold on the idea of doing it. So much so that I think it makes sense to define problems much more broadly. I have had, in the Cornell system, we are allowed to supervise graduate students who may be doing their PhDs in other disciplines. So I've had chemistry majors, physics majors, material science majors working with me, and they all bring a unique perspective. And I think I would find it strange to do research without it being cross-disciplinary.
So on a similar note, since you're working with so many different people, I'm assuming that you've probably had experience working with people from diverse backgrounds, from different cultures. Do you find that that is an advantage in increasing research creativity, for example, different viewpoints that people bring to research?
Well, yeah, it's absolutely, and it also is very personally enriching. I've had um, opportunities to travel the world and um, uh, Asia, Russia, Europe, and I think the role of culture in science is probably underestimated. I think that culture influences how people approach things, how they think about things, and I think it brings also an unexpected richness in problem solving.
The question of diversity and inclusion in science is a really big one right now. I'm wondering if you have any personal experiences in that area or you have any thoughts on that topic.
Well, that's probably a subject of a of
Yeah.
a longer conversation. Um, uh, I think the idea of diversity and inclusion has been a goal in the American scientific community for, gosh, 10, 15 years. And it's been, on the lines of women and minorities and even economic diversity. And it's happening slowly, probably more slowly than most people would like. But it challenges us because the numbers are still much smaller than they should be. Um, but I have seen this over a very, very long period of time, and even going back to the generation of my mother and father. So it's a quest.
I agree. It's a very long quest, but hopefully one in which we're making some progress. But you had also mentioned working with students and postdocs in different fields. And because we have a number of student members in Sigma Xi, I wonder if you could sort of generally talk about if you have one piece of advice to give people going through a PhD process. What's your biggest piece of advice for people who need to survive getting their PhD?
Oh. Um, oh gosh. Well, if they're in a PhD program, I think that by definition means that they have achieved a great deal already in science. It's a very difficult process just to get into a program. So at that point, I think it's persevering, being patient. Things, especially in experimental research, they tend to happen all at once toward the end of a thesis where there are lots and lots of failures, and then all of a sudden the world turns to gold. And I've seen it too many times. It's just an amazing thing to behold. Nothing works, nothing works, nothing works, and then everything works. And so sometimes, people get frustrated with the waiting for everything to work, but it generally does. And things generally work out for the best. Although, from a student temperament point of view, it's never fast enough, I'm sure.
Right, of course. Okay, well, we're over by a few minutes, so I'm afraid we're going to have to leave it there, but it's a really interesting discussion. I really appreciate your time very much, and thank you so much for joining us on our Hangout today.
Thank you, Fenella. It was my pleasure.